Hello everyone. So someone in the comment section in one of my previous video commented about bringing some Pathfinder problems from the chapter of rotation. So today I'll be discussing few Pathfinder rotational motion problem. Let's begin. This problem is from Check Your Understanding question number 14, and the problem is about statics, rotational equilibrium, basically mechanical equilibrium, and it involves translation and rotation equilibrium. So the problem says that we have a thin rod of mass small m is welded on the inner surface of a thin walled pipe of mass capital M, parallel to the axis of the pipe. Okay. The composite body thus formed is placed on a uniform slope as shown. Inclination of the slope is adjustable. You have to find the range of the coefficient of friction between the pipe and the slope for which the body slides without rotation. So this question is basically from the topic of statics, and it's rotational equilibrium as well as translational equilibrium. So first of all, you must know the concept of angle of repose, that the limiting condition for this body to be equilibrium is mu less than equal to tan theta. But theta is the angle between the incline and the horizontal. Okay. Now this is a hollow cylinder. So the center of mass of this is at the geometric center of the circular plane. And suppose the mass of suppose small m is situated at an angle theta, and I am assuming this inclined angle to be phi. So I'll say mu less than equal to tan phi. For limiting case, I'll take mu is equal to tan phi, right? So now, basically, if here is the center of mass of the whole body, then it will just the vertical force, that is the mg, will just coincide with the point of the contact, and we know this angle is also phi. So I can say that geometrically that m, the center of mass of the whole system is m r sine theta plus phi. That is, I am considering along this x-axis, by m plus m is equals to x coordinate of center of mass is equal to r sine phi. If this is the origin, so basically this distance is equals to m into r sine theta plus phi upon m plus m, which is equals to r sine phi. Cancelling r both sides, and dividing by sine phi, and expanding the sine theta plus phi, we will get m by m plus m into sine theta cos phi, sine theta by mu. Since tan theta is mu, we are taking the limiting case, plus sine phi cos theta is equal to 1. Thus we will get 1 by mu is equals to m plus m by m cosec cosec theta minus cot theta. Well, I need to find the minimum value of mu. If mu is minimum, then d mu by d theta should be 0. If I differentiate this whole equation both sides with respect to d theta, well, I will get 1 by mu square negative 1 by mu square d mu by d theta is equal to 0, which is equals to m plus m by m small m. The differentiation of cosec theta is negative of cosec theta cot theta plus cosec square theta is equal to 0. So I will get, dividing both sides by cosec theta and multiplying with sine theta, I will get cos theta here, and here I will get 1. So cos theta will be small m by m plus m. This is my result. Hence, I'll just substitute the value of all these variables, and first we'll find the value of sine theta, which will come out to be under root m into m plus 2 times of small m by m plus m whole square, or just taking out small m plus capital M outside the whole square root, we will get this equation. So this is sine theta, and sine theta by mu is equals to m plus m by small m minus small m by capital M plus small m, which will give us capital M into m plus 2m plus m by m into m plus m. Cancelling all the required terms, I will get mu is equals to m by under root m into m plus 2m. Now this is the limiting case. Of course, the friction coefficient is ought to be greater than this value, or else we will not get the desired result. Hence, friction coefficient must be greater than this value, or else the system will basically slip. And since it's asking that the system should slip, that is why we must keep less than equal to. If the question was regarding that the system should be in equilibrium, then it would be greater than equal to, else it would be less than equal to. So hope you get this problem. Moving ahead to the next question. So this is another question from Check Your Understanding, and this is question number 32, and the question is related to impulse momentum. One may think of work energy, but here work energy will not be applicable because heat is lost in form of heat. Sorry, energy is lost in form of heat. So that's why work energy will not be applicable. So first of all, let us read the question. The question says a homogeneous plank of mass capital M and length L is gently released on an inclined rolling mill, which consists of large number of uniform horizontal cylindrical rollers. The axes of the rollers are fixed to each other in front another in a plane inclined at an angle theta with respect to the horizontal, and separation between each field center is given as capital M. Okay. The mass of the roller is m, and each roller can roll without friction and acquire acceleration, and each roller can rotate about its axis without friction and acceleration due to gravity is g. And after a long time, it said that the cylinder acquires a constant speed. We have to find this steady speed. Okay. And it is also shown that there is a small gap between successive cylinders, right? This basically implies that whenever the roller is or the plank is rolling between some cylinder, the cylinder with which it's not touching does not get affected. Now we will make a small assumption. The assumption is very simple. That is, roller attains a steady omega almost in a short time. Now what happens here is that, suppose the last roller on which the plank is touching, I am making the plank with a green color rather. So this is my plank and these are my cylindrical rollers. So the last roller on which it's touching and the successive roller, the distance is smaller. Now since we assume that the plank is moving with constant velocity, so the time required will be L by V. Now force on it will be mg sine theta. So in this interval, the impulse given by the gravity jg is written as mg sine theta into t, that is L by V. This is equation 1. Now when the green colored plank steps on the next cylinder, what happens is that it will attain some omega, and omega is given as V by R. Right? The situation will be just symmetrical to the previous frame. Means this frame and these two frames are symmetrical, so there will be some impulsive friction on it, on the roller, so that it will gain some omega. And we know that for a cylinder, the moment of inertia is given as mr square by 2, and since it's a solid cylinder, so it will be mr square by 2. Thus mr square by 2 omega is given as f into r, jf into r. So I will get jf is equals to mv by 2. Equation 2. Well, it will be small m, pardon, and here it will be capital M. because it's mentioned in the question probably that you have to consider the mass of the cylinder to be capital M, mass of the cylinder to be small m, and the plank to be capital M. So I will get Jf is equals to mv by small mv by 2, and we know that these two terms should compensate each other, else the cylinder will keep accelerating rather than attaining a constant speed. So small mv by 2 is equals to mg L sine theta by v. Hence we will get v small v is equals to root 2 mgl sine theta by m. Hence we get our final result. Hope you understood the problem. Moving ahead to the next question. So this is the last problem of today's session. The problem is actually based upon scaling, and the problem says a light rigid rod is pivoted at its lower on the ground. The rod is turned to make an angle theta with the vertical, and a bead of mass small m is affixed at its upper end, as shown in the first figure. When the rod is released, the bead hits the ground in the time of t naught. Now, an additional small bead of mass eta m is affixed at the midpoint of the rod, and the rod is again, well, there's some words missing probably in the other page. I'm writing it. It said that rod is again released from same angle theta with vertical in second figure. You have to say the time required to hit ground in this case. Basically, we are given the time required by the rod to hit the ground in the first case, and we have to derive the time required for the system to hit the ground in the second case. Basically, the consideration is about the approach. First, what we will do, we will be using energy conservation. Suppose when the system makes angle phi, and since the rod is light, we can ignore the contribution of rod's moment of inertia. So in the first case, what we will be discussing is work done will be mg l 1 cos theta minus cos phi, right, is equal to half into m r square by 2 omega square. It will be mr square only, sorry, mr square omega square, yeah, l, because length of the rod I have assumed it to be l, ml square, and cancelling l both side and an m, I will get omega is equals to root 2g cos theta minus cos phi by l. And we know that omega can be written as phi dot, which is equals to d phi by dt. Hence d phi by under root cos theta minus cos phi integral into root L by 2g will give me T naught, and this integral is carried from theta to pi by 2. I consider this whole integral to be some I. I can write it as root L by 2g into I. So this is my first equation. Now in the second case, my moment of inertia will basically change. And similarly, the work done by gravity will also change, because it's written that when in the second case a bead of mass eta m is fixed at the midpoint. So in the second case, suppose my system has descended by some angle phi. Eta m is affixed at the midpoint, and here's a mass small m affixed here. So in this case, work done by gravity can be written as eta mg L by 2 cos theta minus cos phi plus mg L cos theta minus cos phi, which will give me eta plus 2 by 2 into mgl cos theta minus cos phi as the work done by gravity. And the kinetic energy gained can be written as the moment of inertia of the system into half, and the moment of inertia will be eta m l square by 4 plus m l square into omega square. Just further more simplification, you will get 4 eta plus 2 upon eta plus 4 into g by l. Yeah, then we will get omega under root will give me into cos theta minus cos phi will give me the value of omega. Now just we'll be again doing the same integral. D phi by dt is equals to 2 under root eta plus 2 upon eta plus 4 g by l into under root cos theta minus cos phi. Now multiplying with dt both sides and integrating and dividing by another factor, that is cos theta minus cos phi. Integrating both sides will get 2 root eta plus 2 by eta plus 4 into g by l into time t dash, I am assuming, is equals to I. And in previous case I found I is equals to root 2 g by l into t naught. So I'll just substitute it here, equal to root 2 g by l into t naught. 2 g by l cancels from here, and a root 2 also. From here I'll get t dash is equals to t naught into root eta plus 4 by 2 eta plus 4. And that's the answer to the given problem. So this is the solution to question number 29. Hope you enjoyed it. So that's it for today. Thank you. Have a nice day.